things that are, for instance, highly electronegative
I kind of want to just.
have a high value for that, it means that they are much more likely to react with other substances. The small elements, physically, atom that is small is more likely to react than a molecule that our element has a large configuration. And you need to remember this, that the noble gases are an exception to these rules. Okay, let's move forward. Bond polarity. This is hydrochloric acid, HCl.
Fun.
And the chlorine pulls on the electrons a lot more than the hydrogen does. And what happens is this side ends up negative, and because this side ends up negative, this side ends up positive. And it's because this nucleus has enough neutrons in it, protons in it, that it pulls the hydrogen electron towards it. And that's what causes this bond polarity. Okay. Now what they're talking about here is if we had a hydrogen atom and you have two of them, you'll get a bond between them, and that's why it's so often hydrogen is found as H2. But the the electromagnetic pull from each hydrogen is the same, and so this is not bonded. This is not polar. Pretty much the same down here you have an oxygen and a hydrogen, and the oxygen pulls much more on the electrons than the hydrogen does, and so this is called a polar covalent, meaning that it has been, electrons have been shifted one way or the other. Covalent is talking about the fact that you have covalent electrons, which are the electrons in the outer shell, and that they can be shared. We're not talking about ionic here, we're talking about sharing electrons. And so that's where the term covalent comes. The next step up is when you have a big difference between, no, that was my fault. I got too close to the screen. With NaCl, there's a big difference between the electronegativities. No, they don't have it on this chart. And it actually pulls an electron off. The chlorine attracts electrons much more strongly than sodium does, and so it tends to pull that electron completely off, and that's what we call an ion. Ions are not something weird and strange, they're everywhere. They're a perfectly normal part of nature. The one that has the larger negativity is the one that's going to end up with the negative charge. Ionic versus covalent bonding. Ionic is mainly metals to nonmetals. These things have high melting points and boiling points. Oh, covalent, ionic. They make crystalline networks. I'm going to show you one in a little bit. I think they've got it. If not, I'll do it at the end. And they become electrolytes in solution. They don't conduct electricity when they're in that form, when they're in a solution form. And there are examples right here. Metals and nonmetals, high melting and boiling points make crystalline networks, are the main points there. Over here on the covalent, covalent is almost always nonmetal to nonmetal. It has, these substances have lower melting points and boiling points, and they don't have to have a crystalline structure between atoms. And they have different kinds of shapes such as linear, bent, etc. They're not going to ask you specific questions about that. They don't conduct electricity, because what are the things of, if we say something's conducting electricity, what type of things conduct electricity? Metals. Not every metal is particularly good at it, but metals are excellent conductors, many of them. Gold is an extremely good conductor, and it has the advantage that it doesn't corrode.
Like you said that they put a thin layer over some stuff.
Mm-hmm. That's right, electroplating. And here are a couple of examples. NH3 is ammonia, and of course, water. Okay, Lewis dot diagrams. They came up with this to make it easier to look at the structures between different atoms. What you are seeing here are the valence electrons.
I've seen these before.
Okay, good. And it sometimes makes it easier for us to understand what's going on. When we have a covalent bond, you're going to see that they complete each other, at least partially. This means
They cannot bond with them.
they don't bond with anything. And Xe is
Xenon.
xenon, an inert gas.
Oh wait, sorry. Oh, that's why. It's because the dots aren't lined up. That's why I thought it looked weird.
No. Now they didn't line the dots up all that well.
We love it not being perfect.
It's useful because it just concentrates on the valence electrons. Okay? They're just saying the same things I just said. We're going to go through this pretty quick. Ionic bond is a bond formed from a transfer of electrons from one atom to another. Here is what's going on in this crystal. The sodium loses an electron, the chlorine gains it. That means that this becomes electronegativity and has a stronger electronegativity than it did when it was just an elemental form.
This is like what I learned about like basics of last year.
Good. I'm glad they do it then. Okay. This part's pretty straightforward. This is the part that I hope we'll get time to talk about it a little bit. But salt forms crystals and they look like that. Their structure looks like that. Covalent bonding is a sharing. Each of these atoms contribute one electron, and they both share that electron. So they end up with 8 electrons. We'll say actually they end up with 7.5. But what that means is it's a more stable atom. The number of electrons, as we'll see, you can tell things about them, how many bonds they can form. But I think it's better. Here are multiple bond examples. Carbon has 4 electrons in its outermost shell, 4 valence electrons. It makes copper the ideal candidate for a covalent bond. And so it shares 2 electrons with this oxygen, and on this side it shares 2 electrons with this oxygen. And that's how you get a double bond. Having a double bond gives it different characteristics than a single bond. And here's carbon monoxide that goes one step further. This has a triple bond. Triple bonds are not nearly as common as double bonds, but they exist. And you see again, now they're sharing more electrons because you're talking about 6 electrons. But then each of them has 2 more, and so they get that octet of 8 that they're looking for. Resonance. Resonance determines these angles. Use multiple structures or resonance structures to describe the molecule. What that means is that there are different ways you could put the molecule together. And those different ways are called resonant structures. Now, the truth is, if we have any of these molecules we said, and we have a number of them, they probably have all the resonant structures in the mix. But we don't have any way of determining that exactly. But it gives the properties of those. There are d orbitals. D orbitals mean you have to have 3 levels. You have to be that 3rd sphere out before you can have it. And you can have d orbitals between the same type of substances that we were talking about. Phosphorus here is another one that is has 4 electrons, and it can share in a lot of different ways. Now, when you look at this, these electrons up here are pushing on these electrons to the side. They're trying to push it away. It's like taking a magnet and turning it so that the 2 positive poles are together. You'll feel a very strong, depending on the strength of the magnet, you'll feel a pushback. Here, these neutrons are trying to pull everything in. So you've got a bit of a struggle here between this repulsion and this attraction. What happens is these end up in different looking structures. This one, for instance, if I remember right, this gets bent down because this is strong enough to push it. And so instead of being like that, it is sort of
like
a
an
Y.
upside down Y.
Yeah. You got it. Vesper. A long time since I thought of that word. Vesper is talking about the various shapes that are formed. And it's another tool that's used to determine what shape things will be. I'm not going to go into it any farther than that because I don't think they're going to cover it in real detail. Okay. Molecular polarity. What you're looking for is ionic or polar bonds. If they are, if you see that in an molecule, then it has polar bonds. If you don't see any of those, it's nonpolar. Now, you look at that one that's on the screen, and it definitely would appear that that's has enough electronegativity going on there that it probably is bent. And if that's the case, then it's polar. Because you're going to set up one side is positive and the other side is negative. Hybridization. This is when we take the orbitals for two different levels, like S and P, and the two merge together and end up in a different shape than either the S's or the P's. And that is hybridization. We've got a hybrid shape. And you can, now they've got some other examples here. And you can see what happens. These two go together and you end up with that. But it explains why they have those particular structures. And here are just a couple more examples. I don't expect you to memorize those or know them. Sigma and pi bonding. Hybrid orbitals. That's the first thing. It has to be a hybrid orbital before this can happen. They can be called molecular orbitals. There's something called the true molecular orbital, and that is not going to be covered in any way. I agree that it is well beyond the scope of this curriculum. I didn't even hear about it until I was a senior in college. It never came up in any of my chemistry classes until I got to the fourth year. Sigma bonding is head-to-head overlap. Head-to-head, they mean that they're overlapping like this, right here. And pi bonding is side-to-side, like these. Like those right there. And over here.
So,
And that again describes the shape.
so sigma bonding. Okay, so pi bonding is non-hybridized orbitals, but sigma bonding is atomic or hybridized.
Absolutely. There are some exceptions, but that's the rule to go by. The exceptions are not common. Lady said that.
For the
Yep, they said that.
For the unhybridized ones, what's with the like plane in between?
This is the pi bonding.
The ones there,
Which one? Here?
down,
Down? This one?
yeah.
Okay. These are definitely sigma bonds because this, looking at this would have it would be a bent shape. And you need that to do hybridization. And the other thing here is like this one, if you rotate this around the center, it's very likely that these parts will fly off. They're not held that tightly.
Why the bean shape?
That That's just, those shapes come from physics more than anything else. And that is, they've done a lot of experimentation. Here's a charge, and we measure the electromagnetic field in hundreds of places in there to find out what the shape is. And as you put that all together and graph it, you get a shape. Now, it's more complicated because these shapes are all three-dimensional. We're gonna stop in a minute on this stuff. Don't worry about that. Okay. I have to cut some things out. Okay, here are the last two slides we're gonna look at today. These bonds, these all of this physical property where they're being bent out of shape and hybridized and all of that kind of stuff has forces all throughout the molecule. Those forces are called van der Waals forces. And they hold the molecule together more than you would expect.